In this video, we're going to go over the initial rate method and how you can use it to basically calculate everything about a reaction. And so the question is up here. It says, what is the rate law expression? Which means we're going to find the individual orders with respect to each of the reagents, and the specific rate constant, which is that little k that's in the rate equation. So you're going to have a table like this in order to get started. Some tables are larger than others. This one's a pretty good size. And it depends on who's set up the data and done the experiment as to how quickly it's going to be able to figure out which place to start. Now, ideally, what you'd have is as many reagents. You'd have that many times 2 trials, and so you just have 1 pair of trials for every single reagent, and you really wouldn't have to think about it too hard. But that usually isn't how it's done. Usually what is done is you have to go through and look and see which would be the best place to start. So sometimes there's more than one place to start, so it doesn't really matter if you don't start in the same place as someone else. What matters is you end up getting the same results. So the basic starting point is, since we don't know any of these at all, if we write out the rate equation, every single reagent A, B, and C is going to have an unknown power, in other words, an unknown order. All we'll know is that the unit in this specific rate constant so far, all we'll know is that it's per time, because of course we've got per second data here. So let's look at what we have. And if we look at our different trials and we go through and compare, we can see that in experiments 1 and experiments 3, if we look, we have the same concentration of A, we have the same concentration of B. That's not true of experiments 1 and 2. And we have a different concentration of C. So that is a good starting point. If we look at other places, we don't always have the best situation there. We want to make one starting point where only one reagent is changing. And there's a reason behind that. So what I'm going to do is I'm going to write out the brute force way of doing it, and then we'll go through and sort of do the by inspection method. So what I'm going to do is I'm going to write the rate equation down here. So let's go see how we do that. So we can write rate equals, then we're going to have K, A, we're going to use X, Y, and Z, because we just don't know what they are. Now, this would only be of use if we actually knew all the individual bits of data. So since we don't know really anything yet, what we do is we write it twice. And we can divide one equation by another. So I'm going to write it again, and then I'm going to add some other bits to it. All right, now let's think about this, what we decided already. We decided, looking at this, that trials 1 and 3 were going to be a good starting point because the only thing that changed was C. So if we look at this, we can go 1, 1, 1, 3, 3, 3. This is just a label to say trial 3. So let's label those as well. The thing is, K is going to be the same no matter what trial we talk about. So immediately, K cancels. So even though we don't know what it is, it doesn't matter. Then we can go back and we can look at our data that we actually have, and we can then just update this, and I'll show you how it works. So I'm going to go move this off to one side, the table, and then I'm just going to be copying from the table. We got a screenshot at the beginning, so you should be able to go back to it if you need to. So we're going to do rate for experiment 1. The rate for experiment 1 was 2 times 10 to the minus 4 molarity per second equals, I'm already going to not, whoops, let's zoom out. Okay, so I've zoomed out, and what we're going to do is start filling in the numbers from the table into this expression that I set up for experiments 1 and 3. So this is the initial rate of formation from experiment trial 1. I'm not going to bother to write the K because we've already decided it's going to cancel. Then we can put in the concentrations. In experiment 1, this was 0.2. And I'm not going to worry about putting molarity on the side because we already know the units of molarity, and I'm just trying to not make it too messy. We're going to put X here because we don't know what it is. Then we have 0.1. Again, we put this to the Y. And then the last one we have is 0.1, and it's to the power of Z. And now we're going to do the stuff for trial 3. So make sure you pull the right numbers out of the table, obviously, otherwise this isn't going to work very well. So then we look at trial 3, and we have 2 times 10 to the minus 4 molarity per time equals, and in trial 3 this is 0.2, and this one is 0.1, and this one is 0.3. So then we can start seeing, so that's my handwriting there, then we can start seeing how we can work with this. Now in this case, we actually have a situation where these numbers are the same, so this whole thing's just going to cancel and equal 1. If it didn't equal 1 though, it's going to equal a number, and therefore we can just solve that problem quite simply. We just use our calculator if necessary. Now look here, we don't know what x, y, or z are, but if we look at this, this is 0.2 to the power of x, and this is 0.2 to the power of x. So even though we don't know what x is, this is all going to cancel. Same thing here, this is 0.1, and this is 0.1, so these cancel as well. So it really doesn't matter what x and y are, because whatever we raise them to, say this was squared, this would also be squared, this whole thing's going to cancel. So that's why we get rid of it all. So if we look at what we've got now, it's really simplified down. What we have is 1, that really simplified, if not it would have been just a number, is equal to 0.1 over 0.3, and again, if they're to the same power, that's a z, it's my terrible handwriting, this is to the power of z. So we've got 0.1 over 0.3, in other words 1/3, so 1 equals 0.33, reoccurring to the power of z. Well, if you want to make 0.33 the power of something equal 1, it must mean that z equals 0, because anything to the power of 0 is equal to 1. And if not, you have 2 options open to you. Either you can sit there and take natural logs of things, or you can try by inspection. And most likely this power is going to be 0, 1, or 2. So quite usually you can just sort of trial and error it. But again, if you wanted a absolutely foolproof way of doing it, you would take natural logs of both sides and use property of logs, because you could bring this out at the front. So what we've done is we've determined that z is 0. So what this is 0th order with respect to, and then remember the reagent that this goes with is c. So now we know one of the orders. And if it's 0th order, that means in the rate equation, c won't show, because it'll be to the power of 0. So what this immediately does, if we go back to the table real quick, is then greatly simplify it. Because, if I go back up here, if this has a order of 0th, it really doesn't matter what you do with these concentrations now, because it's going to have no effect whatsoever on this rate. So as we can see here, these aren't all the same values. Some of these numbers are quite a bit different. But it really doesn't matter what this is doing, because that's what 0th order means. I can make this whatever number I want, as long as I've got some. What happens over here, any change in this from one trial to another has not been caused by me changing c. So essentially, I can just kind of ignore this data at this point. So if you look at that, that does kind of, change what you might want to do. But let's say, for example, that we want to keep going. If we look at, say, for example, experiments 1 and 2, now we can see that although there are 2 things that change, B and C's concentration between trials 1 and 2, the fact that it's 0th order with respect to C means this doesn't matter. There's no need to be worrying about it. So let's see if we can try doing this one by the method that they call inspection. So this one is a little bit less writing, and it works as long as you can do the math in your head. If you can't, then what you do is you go back to here. You go back to this method, for example here, and then in that case, for example, it might be trials 1 and 2. You can use the same trial over if you find that you need to, or you can use 2 different pairs, whatever is going to give you the information you need. And so once again, what you do is you just feed in all the numbers, and if you have anything you've already calculated, like say we know this is a 0, then what would mean then is that we would just update it. So for example, we can already write now that if we did use trials 1 and 2, let's just show what we would do real quick. We'd have rate 1 equals, I'm not going to bother putting the k in because we know that cancels. We'd have a1 to the x, b1 to the y, and I'm not going to need to write z because we've already determined C is whatever it is, but Z, the power, the order for C is 0. We have rate 2 equals, and then we're going to have A2 to the X and B2 to the Y. Sometimes I put the label in or outside of the brackets. It's just a label. It's not a power, so it doesn't really matter exactly where you put it. All right, so let's go back to looking at doing this by inspection, because again, what you could do is you could then just pull the numbers in from this, stick them in here and do the exact same thing I've done before. But let's look at the other way of doing it, which is the by inspection method. So we were going to use trials 1 and 2. So if we look at trials 1 and 2, let's zoom in a little bit so we can look at it again. Trials 1 and 2. Okay, here we go. In trial 1 and 2, A didn't change. So whatever is happening over here is not being caused by A. So that would be the idea of, once again, we could cancel A if we were doing the dividing rate equations, the brute force method. We already know that the power for C is 0, so it doesn't matter that this doubled. It has done nothing to the rate. Now we can see that this obviously isn't the same, unlike it was in trials 1 and 3. And if you look at this number, you can obviously see that trial 2 is 3 times the value of trial 1. So the rate has tripled. And if we go here, this is 3 times. So let's go back to our paper where we were summarizing and see what we've got. Okay, so trial 1 and 2. So we're going to just summarize. A, no change. C, 0th order, no effect. And then we have B, and it went tripled, going from 1 to 2, comparing, and the rate tripled, going from trial 1 to 2. So if you notice, we have the same thing. We have a direct dependency. So direct dependency that's first order. First order is there's a direct dependency. If I quadrupled the concentration, I'd quadruple the rate. Here I tripled it, so the rate tripled. So now I know that basically going up here, Y is equal to 1. So I've got Y and I've got Z. So at this point, you've got all kinds of options as to how you find X. Let's just pick out a couple, for example, of what you could do. You could pick any trial you like now, because you've got all the data except one thing. So you can just pick out any two and put the data in. If you wanted to, you can also include one where your B changes, because you actually know the dependence on it. But if you want to make it simple, of course, if you want to try to find one where only one thing changed, then the one that makes the most sense, if we look at this, is trials 2 and 4. You're trying to just make it easy for yourself. If you look at trials 2 and 4, B doesn't change, C does, but we've already shown that that has 0th order, and this one changed. So again, what we can do is we can write the two rate equations out. We can feed all the numbers in. We're going to see B cancelling. C is going to be to the power of 0, so its concentrations will just be rendered 1 because they'll be put to the power of 0. And then we have these two values. So this has tripled. And if we look over here, this is where you've got to be careful when you're reading these in scientific notation. Zoom in just a tiny bit. You'll see this is 6 to the minus 4, and this is 1.8 times 10 to the minus 3. In other words, this is 18 times 10 to the minus 4. So this also has tripled. So just be careful when you're reading your exponents, that you don't make a mistake. All right, so let's add that to the summary, and then we've got everything in terms of the orders. So trial 2 and 4, okay? So we can say A going from 2 to 4 tripled. It went from 0.2 to 0.6 if you go back and look at the data. We can say that B no change, and C, 0th order, so no effect. So let's see, A tripled, and let's see what the rate did. Rate tripled. And so once again, this is a direct dependence. And so therefore, first order, so x equals 1. So now we know all of the orders. And again, if you wanted to, you could do something like you have here. We can write out for rates 2 and 4. Once again, we don't have anything here because C is to the power of 0. We would now know that this is 1. And it turns out if we pick trials 2 and 4, of course, both of these numbers were the same, so it cancels anyway. But even if you didn't pick trials 2 and 4, if you pick, say, trials, let's say you picked trials 1 and 4, you can still sit there and you can say, well, in the case of trials 1 and 4, this would be 0.1 and this one would be 0.3. You just make yourself a bit more math, basically. But you'd know now y is to the power of 1. So you just have to set 2 and calculate that piece out, as well as doing that over here. So again, if you can, why make life more difficult? Try to pick pairs where only one thing changes, or if something else changes, it's something you already know it's 0th order. The less you have to do in the way of math steps, the less likely you are to make a mistake. That's really what it comes down to. All right, so we've got all of our orders figured out. So let's write out our rate equation that we know as we know it right now. We're going to say rate equals, I haven't put a specific number here because I'm going to write this as completely as I know it and as generically as I know it. So it's going to be A, and because we know this is first order, we just don't write anything, of course. And we have B. And we don't write C because it's 0th order. So that's the equation that we know. Now, here's the really cool part. What we have to do now is actually find out what K's number is. We actually can figure out what its units should be, because if you think about it, this has units of molarity squared, because this is molarity. They're both to the power of 1. This had units of molarity, and in the case of this experiment, it was per second. So you can actually now see what the units have to be for K without even finding the value of K, because if this is molarity squared, this must be molarity to the minus 1, so that one of those cancels and just gives you molarity, and then per second. And being able to figure out either the units given the overall order or going the opposite direction is really key, because if we don't actually give you the rate equation, we just give you the units of K, you should also be able to figure out, well, this is indicative of second order overall. Now notice, if you're just given the units for K, there's no way to know that there's two separate things, each with an order of 1. There's no way to know that if you're just given K's units or a value of K and its units. But what you can say is it definitely overall has to be second order. And there's more than one way that could happen, of course. Now to find the numerical value of K, the beautiful part about this is it absolutely does not matter which trial you pick. You can pick whichever trial you want. And if you don't believe me, I'm going to do one of them, and you can just, do a different one and see what you get. So let's see, here we go. We're going to just rearrange this. It's going to be K equals rate over A, B. I just rearranged up there. And then I'm just going to stick some numbers in. Let's see, they're going to use trial 1, I think. So we're going to have 2 times 10 to the minus 4 molarity per time over, and then we have A is 0.2 molar, and then B is 0.1 molar. And again, technically, if you want to put the C in, you'd be raising it to the power of 0, which means there'd just be a 1 here, so there's no need to be doing that. And once you've done your math, you'll notice that the molarities, one of the molarities goes away, and we're just going to end up with molarity to the minus 1 times to the minus 1, just like we predicted. And the number that we get is 1 times 10 to the minus 2, and it's molarity to the minus 1, seconds to the minus 1. So now we have everything. If we wanted to just finish it off, we would just write this. Rate equals 1 times 10 to the minus 2 molarity to the -1, seconds to the -1, and then we'd have A, B. And that's our finished rate equation. So that's the basic steps. The more reagents you have, the longer it's going to take. The more the times you can do it by inspection, the better. The worst case scenario is if they give you such a restricted amount of data that you have to look at 2 things changing at once and you can't cancel the concentrations. What you can then do is, again, you've got 2 options. You can either brute force write it out, which might be safest so that you don't miss anything, and put in all the powers that you do know, put in all the concentrations. The other way you can look at it is you can, once again, you can go back to the table and do by inspection, and you can say something like, well, if I already know that it's first order with this reagent and it tripled, then there would be a ×3 effect going on in the rate. And then, wait, it's not just ×3, maybe it's, say, it's ×3, but then it's also ×2. Okay, so something else caused that. Well, which other reagent was it? And then you can sort of factor that in as well, because if another one doubled, then now you've got that going on. A little bit more difficult to do that, of course, but it's possible.